Hello and welcome. So today we are going to look at the regularization. So it basically addresses the overfitting problem. So what is this overfitting? Let me explain you. Let's take these points as your training example. Let's suppose that these are your training example. Now you want to train this model and you want to get the hypothesis, right? Hypothesis function. Let's suppose that you trained your parameter theta 0 and theta 1, and in this case what the hypothesis function will look like is the straight line. That with the given training example, what your model have learned is a straight line, uh, right? And let's suppose that in the second example, with the same training set, you increased your number of features, right? And in this case what you learn is, maybe you will learn with the higher degree of polynomial, that is x squared. So maybe you will learn, your model will learn, and it will give you a hypothesis that may look like a quadratic function, right? And with the higher degree of polynomial, it may happen that if let's suppose that if you have the features, if you have these features that is more number than your training example, then it may happen that your hypothesis will learn to fit each and every example. So this could be the case when you have features, that is number of features that is greater than your training examples, right? So it may happen that if you try to model your training, you will end up with a hypothesis function that will fit your data to every training example, right? So this is what we call the overfitting. So this is overfit. So your hypothesis function have perfectly fit into your data, and this is what we call the underfit. And this is just right, we can say, between overfit and underfit, right? Okay, now let me explain you what's the problem with this overfit, right? So basically, if I ask you that you have to make a predictor, let's suppose that given a house size, your predictor should predict the price of the house, right? So which model you are going to select? This is the model 1, this is 2, and this is 3, right? So let me first of all explain you this overfitting problem. So what may happen that let's suppose that given a house size, at this your model have predicted this price, right? This much of price. Now if you think, then if you take the house size of the house a little bit greater than this, maybe here, then intuitively you can say that the price should vary little bit from this size, right? But what your model is going to predict, you can see that your model is going to predict this much of price, right? So you see that the difference between, if you have just varied your size of the house, then this is not a practical scenario, right? If size of house is a little bit bigger, then you can say that price would go a little bit higher, but your model is not a good predictor here, right? So this is the problem with the overfitting, right? So the hypothesis function, the model your hypothesis is going to learn, is not a good predictor in this case, right? So we want to have a model that should work in even for the generalized case, right? I mean to say, for even for the general example that have not been seen yet by your model, it should give a price that should be, I can say that you should convince that yes, the little bit of this much of variation, the price should go a little higher. So yeah, my model is predicting somewhat right, right? So this is the problem with this overfitting, right? So that is one thing. And if I ask you about this underfit problem, what's the problem with the underfit? You see, you will have to look at the trend of your data, how your data is varying, right? You see that for lower price, and if you go towards the higher side, if you go towards the higher side, then your price is going to increase, and after that it is going to be same, right? But what you have learned, what your model have learned is that if you go higher, then it is going to be pick a more higher price, right? So according to data, this is not I can say the perfect fit for your model, right? So this is the underfit, and so overall what we are going to pick is the just right, right? So you see that you will have to make the balance somehow, right? So such that your model should not be in the underfit, or your model should not be overfit, right? And you see what we are doing here, that if you look at the features, right? So somehow if you see that in the second model, in this model, these features are not there, right? So somehow this is going to be maybe negligible, right? If we can manage such thing, then we can avoid the overfitting problem, right? So we will look at this. So this is the overfitting problem in case of the linear regression, right? Linear regression, that given a size of house, you will have to predict the continuous value, that is the price. So this may happen even in the classification problem. So if I take the example of this logistic regression, this overfitting problem may happen in the classification problem, right? So maybe maybe your model could learn, maybe your model may learn something like this, right? So it has classified your data in zeros and crosses, right? And given, so what hypothesis function you are going to get with this is this one, right? And here G is the sigmoid function. If you have seen already that logistic regression, then it will make sense. Otherwise, you will have some problem in understanding, right? And this is one. And if you see that in case of maybe if we take the higher more number of features, then it may happen that your hypothesis function is going to classify each and every. So maybe it will classify like this, right? So you see that with the overfitting, it is classifying each and every data, but what your model have learned is very complex function, right? Your hypothesis function is very complex here, right? So what could be so this is again overfit, and this is you can say underfit, and maybe you can come up with a hypothesis function that would be just right. So maybe your hypothesis function will learn simple, not a complex model, but with the simple model like this, right? So the overfitting problem can be happen in linear regression problem, in logistic regression problem. So for whatever the model we have learned that may suffer from this overfitting problem, and we have to make the balance somehow, right? And we will see that how we can make the balance. And this problem could happen with this SVM, support vector machine, right? So just to give you a visualization, what is underfit and what is going to be overfit. So this you see is the underfit. Sorry, overfit. Why overfit? Because what you are doing is that your hyperplane is classifying your data, each and every data, right? You see, right? But this is not a good hyperplane that we should consider in a real scenario, in practical scenario, right? Because this we have got this hyperplane because of this outliner, right? And I have explained you in earlier classes when we were going through this SVM. Then I have explained you that due to this outliner, this hyperplane got completely changed, right? So this hyperplane is very strict in classifying these classes, right? But we should have some kind of flexibility that let's ignore this outliner and let this hyperplane give some flexibility so that we could have a more good hyperplane that should classify your data in general cases. General cases, I mean to say, it should be able to classify, should have the capacity to classify the new examples or the new data which your model haven't seen yet, right? So if I ask that in general scenario which model you are going to pick, then obviously you are going to pick this second model, right? So this is again overfit in SVM, and already we have seen this that in SVM, right? So how we are going to deal with this overfitting problem? So that is what, if we have too many features, the learned hypothesis may fit the trainee set very well, but fail to generalize the new examples, right? That is what I'm saying. Okay. So this overfitting problem generally happens if we have a lot of features but very few examples, very few training data. So how we can address this overfitting problem? So if you have got some idea that somehow we are reducing this number of features, right? So what we can do, so we can have maybe to address the overfitting problem, we can reduce the number of features, right? You see this model and this model, right? So we can reduce the number of features, that is one thing. So manually select which features to keep. So then again we will have to make the decision like I want to keep this feature or I want to neglect this feature during, right? So that is one thing, and that is the one thing we can do, right? Reduce the number of features. But with this we have the problem like how we can make the decision that which feature is more relevant than other feature, right? So there could be so it would be hard to make a such decision, right? If we have, let's say, maybe if we could have 100 or 1000 features, if we have 100 trainings or 100 if we have the 100 what I can say that features, then with that we will have 101 parameters, right? And with this 100 features, it would be very hard to make a decision that which feature is more relevant than other feature, right? But we can do that we can reduce the number of features and we can keep our model simple. And that is one way to avoid the overfitting. And the second is the regularization. So in regularization, what we are going to do is keep all the features but reduce magnitude value of the parameter theta j. So what do I mean to say? That let's suppose we have taken the same example, right? And let's suppose that this is what your model have learned this, right? So what do I mean by that? Keep all the features. So we are going to keep all these features, right? But what we are going to do is that reduce the magnitude of this parameter. So what we can do is maybe we can reduce this theta 3 to maybe very near to 0, right? And approximately 0, not exactly 0, but approx 0, and we can reduce this magnitude to maybe approx 0. So if we do that, then we may end up with a hypothesis that may look like this, right? So what we can do in regularization is keep all the features. You do not have to remove completely these features. What you can do, you keep this feature and reduce the magnitude or value of these parameters, right? So this works well when we have a lot of features, each of which contributes a bit to predict y. So since we are not completely removing these features, we are somehow keeping these features, but weightage of these features in predicting the y is, I can say, they are contributing but very less, right? So this is what the second point is. Works well when we have a lot of features, each of which contribute a bit to predict y. Right? So this is the overall idea behind the regularization, right? So this is what I have explained you that so in linear regression, that is the cost function, right? And this cost function we want to minimize, right? And if somehow we can keep this theta 3, theta 4 near to 0, right? We are not exactly going to remove this, but if somehow we make this approximately 0, then we may neglect these features, right? So a small value for parameter, if we keep this parameter value is small, then what we are going to give is the simpler hyperplane. So this is the hyperplane we are going to get, right? And if and that will lead to the less prone to overfit, right? Okay, so now so far we have also learned about a lot of algorithm, like a lot of models like linear regression, logistic regression, and SVM, all this thing, right? So how we can make the modification in the cost function such a way that we should be able to introduce this regularization, right? So what I'm going to do is whatever the cost function so far we have learned in different models, I'm going to introduce this regularization term, right? So let me first of all go through this linear regression. So in linear regression, what was your cost function? So for that you will have to again go through this linear regression. I have already in first or second lecture we have already gone through that, and there we saw that this was your cost function, right? And this was the cost function that we wanted to minimize, right, over this theta, right? And since we are introducing this regularization, then our extra term is going to be there, right? And here this lambda is the regularization parameter, right? And this theta is again your model parameter, right? So this is the term that we are going to introduce if we want to have regularization in your model, right? And this lambda is the regularization parameter. So this lambda, so let me explain you that how this is going to be work. So you see, this is your objective function j theta, right? And this is your optimization problem and you want to minimize this, right? And whatever the value you will get have the minimum value for the theta, then that will be your optimal value for the theta, right? Now, so you see that this term, what it tried to do, it tried to fit the data well, right? So this term will try to minimize the error and it will try to fit the data very well, if it, right? And this term, right? So this term, so it depends on this lambda, right? So let's suppose that this lambda is very high. Let's suppose this lambda is approximately 10 to the power 10, or you can say the very high, right? And you have to overall also keep in mind that what is your optimization problem. You want to minimize this j theta, right? And if this lambda is very high, right, then the focus of this j theta in the optimization problem to minimize this j theta would be more on this term, right? Because this lambda is very high and you want to minimize this, then your in optimization problem it would be more focus on this term rather than this term, right? So in this case, what we want, if we want to have this minimum j theta, then this theta is going to be very less, right? So this lambda is very large, right? And the more focus would be on this term because this has grown and we want to minimize, then we will pick a theta such a way that this summation is going to be very less. So theta will be approximately 0, right? So that is the one thing. And let's suppose that this lambda is 0, that is very less, right? So now the optimization problem would want to minimize this j theta. Then since it is 0, then the problem would have more focus on this term, right? And this term, what it tried to do is it tried to minimize the it tried to fit the data by minimizing the error, right? So that is the two cases, right? So if you see that this lambda is keeping the control between two things, right? Either you penalize this theta, right, by keeping the lambda very large, you can penalize this theta, you can keep the theta very less, or you can pick this lambda very low, and you can fit your data. You can fit your model into data very well, right? So lambda have this power. If you are keeping this lambda very high, then you are going to penalize this theta parameter, and that is good for your addressing the overfitting problem. And if you want to keep this lambda very low, then your more focus would be on that means you want to learn your model such a way that it fits into your data, right? So this lambda controls the trade-off between two goals. So this goal one is we want to fit the data well. So this is the goal one when lambda is approx 0, and goal 2 is try to keep the parameter value very small when lambda is very high. Then we want to keep this theta very low, or you can say you will penalize the theta, right? So let's suppose, so again the same thing, if theta is very large, then you will penalize your parameter by keeping the magnitude of your parameter very low, like theta 1 is approximately 0, theta 4 is approximately 0. So right, yes, and so you have penalized each and every parameter, right? Then you will end up with h theta that would be equals to theta 0, and this is what your hypothesis function would look like, and this will lead to underfit, right? So, and if you have this, so overall point is that you need to select this lambda, this regularization parameter, right? You cannot keep it very high, because you will end up with every parameter approximately 0, and you will end up with this kind of situation, right? And if you keep this 0, then you will end up with the overfitting, right? So you want to select this lambda parameter. Then how we are going to do that? Then we are going to do the cross validation, right? So if you have already seen that cross validation, then you know that how to pick this parameter, right? So good choice for lambda, what we are going to do, you are going to select a model by using cross validation. So you are going to do the cross validation, and you are going to pick the optimal value of this lambda, and that lambda will such a way that it will balance your overfitting and underfitting problem. Okay, so that was in the linear regression, right? So we can introduce this term, and we can have some kind of balance between overfitting and underfitting. Okay, now, so we have seen this one, right? So this one is the same thing, linear regression with regularization. So we can introduce this term, and you see this is your cost function. So you have already gone through that, how to get the optimal value of this parameter, right? By using the gradient descent. What you can do, you can run this, and at the end you will have this theta value, right? So since there is change in your cost function, then obviously that the update rule is going to be changed a little bit, right? So what you are going to change is this term, and for this is for theta 0, it is going to be same, but again for theta 1, theta 2, theta 3, it is going to be changed. So up to this is you have already seen, right? In the update rule, if you have already gone through the lecture, then if you have seen, then this was your update rule. Now due to regularization, due to this term in update rule, what you are going to see the change is this, right? So I'm not going to get through the again. So I have already iterate through this example. So I have shown you that how we are going to update this theta, and how does that affect, and how does it minimize by so if you have already gone through the lecture, then you will have idea that what I'm talking about, right? So I just wanted to show you that what is the change you are going to get if you are introducing this regularization, right? And we in linear regression, we have seen one more method, that is normal equation, right? And due to normalization in theta, what you are going to see the change is this, right? So earlier, without regularization, the normal equation, that at the end your theta was this x transpose x inverse x transpose y. So that was what your theta was. So it is not your plus, right? So now due to regularization, this term is going to be introduced here, right? And so in normal equation, if you have already gone through the lecture, I have also covered this one. Then this x is nothing but your matrix of your input, right? And this y is your vector of your output, and this matrix that you are seeing, that will be of n+1 into n+1 size, right? And this lambda is your regularization parameter. So this is the change you are going to get if you have introduced this regularization. And in logistic regression, this is what your cost function was earlier, right? And due to regularization, this term is going to introduce, right? And this is what we log loss, what we call is this term is a log loss, right? Log loss, right? So in logistic regression, this is the term you are going to introduce in your cost function, and how you are going to get the optimal value. Again, you will learn run this gradient descent, and you will get the optimal value of theta in case of logistic regression 2. So this is going to be the same update rule, right? But there will be change in hypothesis function in case of logistic regression, and in case of logistic regression, what would be the hypothesis function? You can let me know, right, in the comment section. Okay, and last lecture we have also seen in SVM, right? This was your objective, right? And here we do not have to introduce any new parameter, right? Okay, so So this was your cost function, right? And if we follow the trend, like you see that we have our cost function here in linear regression, this and this regularization term, and in normal equation we have this cost function and the regularization term, and this logistic regression we have this cost function and this regularization term. Now if you see that this is going to be your, so in normal cases this without regularization, this is going to be your cost function, right? And with regularization this term is going to introduce. Now in SVM, so this is your loss function and this is your regularization term. So you can take this C common and you can put here 1 by C, and this C will, so here you see this lambda, so so you can replace with this lambda by 1 by C, right? So that is all about the regularization. So I gave you the idea about the regularization, and overall point is that what changes is going to be in your cost function that you have already seen. Okay, I think that is all about the regularization.